Hey Maha, how are you? Can you hear me?
Yeah, hello.
Hi. Oh, you are in school.
Yeah, I finished the lecture now.
Today you are in school, I'm in home.
Because I have lecture with
Yeah.
electrodynamics, so I
Okay.
finished that now.
You have to go back to your office. I see you're coming down the stairs.
Yeah. Today you will apply you'll be there.
Huh?
I say today you will apply the final exam in the UB.
Tomorrow.
Not today.
Not today, tomorrow.
Okay.
I can give it today, but it probably not going to be until later today.
I don't know. I asked Nathan. I think he said today. I don't know. I am not sure.
I think I said Wednesday. Yeah. I think so. I don't remember.
I don't know, but I
Let's see. You are breaking up a little bit, Maha. You might want to go to a place where your internet is strong.
Good afternoon, Professor. How are you?
Hey, I'm well. How are you?
I'm good.
David, why are you a judge?
Oh, I forgot. I did a judging for a Lego robotics competition, and I forgot to change my name back. Let me do that real quick.
Oh, no. Then wait a minute. How do I have some lawyers here? Okay. Alex might be late, he said, but otherwise we should be okay.
So, Professor, did you decided when's the exam will start and end?
I said I'll give it tomorrow, Wednesday. So I'll give it to you guys tomorrow. And I think time until Saturday is enough. So probably midnight Saturday.
Can you make it Sunday?
Can I make it Sunday? I would rather not, because that gives too much time. Why? What do you have?
Because I have exam tomorrow and exam Friday, so I would just
Yeah.
I would do it on Saturday, and I just want an extra day.
You have exam tomorrow. Tomorrow is Wednesday, and then you have exam on Friday. Thursday you don't have an exam. Thursday of class. I'll be doing the last bit of it. So I don't want to give students too much time. So then I might have to give it on Thursday.
Okay, this would be good too.
I don't want to give them Thursday to Friday. I don't want to give them beyond 48 hours, because then the exam becomes much easier.
Okay, from Thursday to Sunday would be great. Yes, thank you.
Thursday to Friday, Thursday to Friday, Friday to Saturday. You're still getting 3 days. Still getting a day more than I want to give, because you get 2 weekend days. So
Okay, what I care about it ends at Sunday. I don't care when it starts.
you don't care, but others might.
Okay.
So let's have a quick talk as people join. So
At least for my schedule,
Ah,
I have my presentation for my many bodies course on Friday.
mhm.
So if we actually if we took Wednesday to Saturday and shifted it Thursday to Sunday, it would give me a little bit of extra time where I
Extra
wouldn't be.
time. Okay,
Yeah, I wouldn't be focusing on two sort of
okay.
final things at the same time. So it would
No, I
benefit.
understand. That's
Yeah.
fine. How about others? Maha, do you have any issues if I give it on Thursday till Sunday versus?
No,
Okay. Cameron, do you have any issues? You're muted, Cameron. Uh-oh, where is Cameron? He's not there? Are you kidding me? Okay, Jeff.
I have a test on Friday, so
Okay, so for you
it's
it's
good.
better.
Yeah, definitely.
Okay. I don't know what's up with Cameron. Cameron, can you hear me? Danielle, instead of giving the test tomorrow, the motion is to start it a day later. So they want 2 weekend days. Is that okay with you? Thursday to Sunday?
Yeah, that's fine.
Okay. Cameron, are you there or your microphone not working or something? It's not clear what's on with Cameron. 8, 9. Okay. Okay, we'll get started. Cameron, can you hear me now? No. Where the hell are you, Cameron? Nitin?
I saw that he unmuted and muted himself again. So
I can hear you, sir.
I don't know what is wrong with him. Yeah, Nitin, we are probably, looks like people want 2 weekend days. So instead of making the exam Wednesday to Saturday, we are discussing Thursday to Sunday. Is that okay?
Yeah, that is nice.
Okay.
And
I'm happy.
I had a quick.
Tell me.
So then the oral exam would be Monday now?
Oral exam was planned to be Monday, right? I
Yeah,
forgot about
it would
this
still
one.
be Monday. Yeah.
Yeah, I don't think we'll delay that.
Good.
Let's get it over with. Yeah. Oral exam might spill over a little bit too, so shouldn't be, but you never know.
Mhm.
Cameron is not back. I think he's having some trouble. Poor guy. Okay, so what we can do is we can probably get rolling. Let him join and we can check with him. So what I want to do today is kind of finish up most of the stuff that we need to finish. I'm going to share my screen. Wait 1 sec, sorry. So I'm going to be using my notes only, but it's just that instead of putting the handwritten stuff on the board, it's now on this one. Hang on 1 sec. I have a little bit of a technical issue. Okay, admit.
Cameron just texted me because I asked him and he said that his audio is busted. So
No.
he's going to try to reconnect.
Okay. Can you guys see this, my screen?
Yeah.
Can.
Okay. Alex, we are talking about moving the exam start to Thursday and giving you guys time until Sunday. Is that okay with you?
Yep, that's totally fine with me.
Okay, good. All right, so let's just get started. We have quite a bit to do and I want to kind of finish this up. So just as a quick, first of all, my apologies for not having an in-class today because my roof was going to get done. That was going to get done yesterday, but we had terrible weather. So the roof was going to get done today and tomorrow, but given the weather, they decided to do the whole thing today. So as a result, what happened was I got locked in. I can't even get out of the house without mountain climbing. So as a
It's
result,
like COVID.
what?
It's just like COVID.
Yeah, right. There's literally, enormous heaps of old shingles that were around. I had 3 layers of shingles. Right now, they're cleaning it, but I couldn't count on it. I mean, right now I can actually get out to my backyard, but when I sent you guys the message, I was really panic stricken because there was no way I could get out of the house. So anyway, the good thing is that the roof is actually done. These guys they finished the whole damn roof in literally 8 hours.
How many workers did they have? Did you count?
Uncountable.
Uncountable.
They had 2 crews because they wanted to get it done quickly because they have solar panels. They want to put the solar panels back up tomorrow.
Oh,
So they didn't
gorgeous.
want to clash with this. It was a mess, but it's done now. So anyway, all right. So this is what we were doing, the continued fraction formalism for solving the Liouville equation, as you know. And I'll just quickly go over here. By the way, I have set h bar to, okay, h bar is there. I actually changed this nomenclature a little bit as I went along. So let's not look into this. I changed the nomenclature here in class. I had put in the hermiticity factor by making this ILA the classical part, which is the correct way of doing it. Here I was missing the I when I had originally written these notes up. At any rate, you know that this is the quantum case if it's a commutator, and a classical case if it's a Poisson bracket like here. And I told you that the formal solution is the Liouville operator acting on the dynamical variable. And this kind of a statement that you see here leads you to a short time expansion, which is a expansion in powers of t to the 0, t to the 2, t to the 4, t to the 6, and so on. Do any of you know why there are no odd powers of t in this expansion? When you actually fully lay it out, you can unmute yourself. Who wants to give it a try?
Because once we expand, okay, I will just try, okay? Once we expand the 2 exponents, odd will give even, and even will get even too, so.
Yeah, but physically, why should that be the case?
So it doesn't have time reversals. It have time reversal symmetry.
Yeah, correct. It has time because Liouville equation and indeed dynamical equations are time reversal invariant, right? So therefore, you shouldn't have any change if you change t to minus t. Results should be the same. Cameron, is it working now?
Yeah, I got it to work. Sorry about that.
Oh, no problem. So we were trying to make fun of you. But question is, if we delay the exam Thursday to Sunday, is that okay?
Yeah, that works for me.
Okay.
Either or is fine.
Okay, good. All right. So we just started anyway. So we write A of t in terms of this Hilbert space expansion, where the f's are mutually orthogonal and the a's are time-dependent coefficients. F's are, of course, time-independent. They are like basis vectors. And so I don't know why it does that. So at any rate, this is where I actually took a little bit of a detour as I was doing it on the board. I explained to you that you can pick various schemes for orthogonalization of the f's. And I told you that one of the historically important schemes that was used was this particular kind of scalar product. It's called the Kubo scalar product. I have the name somewhere here, I'm sure. Kubo scalar, here we go, Kubo scalar product. And the Kubo scalar product is actually a pretty complicated thing. It's actually like a susceptibility. But this x of lambda that you see here is e to the lambda h x to the minus lambda h. I may be off by a minus sign. This may be minus, this may be plus, but nothing terrible. No terrible errors here. And of course, the ensemble average is the canonical ensemble average. This problem is being cast in a canonical ensemble setting. I also mentioned that a simpler scalar product is simply the fluctuation formula. And this fluctuation formula is something you can actually recover from the Kubo product, the susceptibility formula, this one, by essentially going to the infinite temperature limit of this one. But that doesn't mean that you can't use this in general for any temperature for a particular problem and be fine with it. Alex had some objections to it, but we decided to ignore him.
Wouldn't be the first time that happened to me in class.
No, because basically this is a simpler one, and sometimes you get away with it, sometimes you don't. And once again, because some of you may have missed it, the issue here is that the scalar product you select is invariably dependent upon not only the Hamiltonian, but also the variable that you are exploring. Okay. For example, if I may have a mass spring chain, and my dynamical variable can be momentum of one particular tagged particle. Let's say I have a 500 particle chain. I might want to look at particle number 45 or 46, whatever. Or I might want to look at a collection of particles, let's say, the velocities of particles, three particular particles I want to look at. That can also serve as a dynamical variable. So you have a great deal of choices. You have completely arbitrary choices in what kind of dynamical variables you want to pick, which makes it a very powerful way of solving this problem. Regarding choice of, this is very weird. Regarding choice of initial conditions, which we select F0, the first of the Fs, to be the dynamical variable itself at time t equal to 0. So that's your initial condition. That's a perturbation of amplitude A, if you will, perturbation of velocity represented by A, if you will, whatever. And for the left side and the right side to agree, agree meaning agree where? Why am I going forward? For the left and the right side, in this thing to agree, you will see if this is F0 and all the other Fs are 0, then this is A0, and at t equal to 0, it must be 1. So for the left and right sides to agree, this F0 equal to A and A0 at t equal to 0 equal to 1 must be satisfied for this condition, our main statement to be valid. All right. So that's what's being captured here. Okay. So it's nothing weird about what we are doing. This is the part where I skipped a little bit, and I come back and fill in the details later because I want to get on to important things. I mentioned that xy and yx, because these are scalar products, this ordering does not matter. I also mentioned that the Liouville operator acting on x comma y is negative of x comma Liouville operator acting on y. So these two properties are important properties. Here is the proof, which I'm going to skip now. You can look at the proof on your own, but I'll try to come back and walk you through it. At any rate, our next goal was to construct the orthogonal Fs. Why? Because that's what we need to do And we have already decided that we're going to use the Kubo product as our mechanism for imposing orthogonal generation of orthogonal vectors. If I ask you to orthogonalize vectors, what is the general scheme that you'll use? You should know this from undergraduate mathematics.
Did you say that one more time for me?
If I ask you to orthogonalize a bunch of vectors, what is the general scheme that you will use? There is a general way to orthogonalize vectors.
Gram-Schmidt procedure.
Yeah, Gram-Schmidt procedure, exactly.
Knew
So
it
what
involved
we-
dot products.
What?
I knew it involved projections and dot products, but I forgot the name of it.
Yeah, the Gram-Schmidt is very important. Don't ever forget the Gram-Schmidt, because the Gram-Schmidt is kind of like your lifeline when you are dealing with vector spaces. So what we are actually doing, by the way, is the sort of simplified Gram-Schmidt. That's what I'm going to show you. This is what I was doing on the board. So the point of it is that if you see that Lxx is minus XLX, this comes from the second of the two lemmas, and Lxx is also going to XLX, then you can see that these two are incompatible, which means that this must be 0, which means that F1 and F0 must be, scalar product must be 0. So F1 must be orthogonal to F0. This was something we did in class. So these two inner products are exactly what we did, what I alluded to in the previous page. All right, so let me just move on. But you not only have to be orthogonal to F0 as F1, but now you have to think about F2 being orthogonal to F1 and F0, right? So what do you do for F2? Let's go back. Okay. So if you want to carry on with this using a Liouville operator to move on to the next vector, then you can try this L squared x comma x. It turns out this L squared x comma x is non-zero. So therefore, the long and short of it is that but L cube x comma x is going to be 0. So it turns out that a series like this will not be an orthogonal series. But x and Lx would be orthogonal, then L cube x would be orthogonal, L fifth x would be orthogonal, and so on. But L squared x, L fourth x won't be orthogonal to the rest. So this is obviously not tenable. You need to do something else. So question is, how do you then construct F2? Okay, and this is kind of where we had been working on, because if you want to construct F2, then F2 should not only be orthogonal to F1, F2 should also be orthogonal to F0. So it has to satisfy 2 orthogonality criteria. Likewise, F3 will have to satisfy 3 orthogonality criteria. F4 will have to satisfy 4 orthogonality criteria, and so on. So to make sure that is possible, now you are going to appeal to Gram-Schmidt. But the way we did it was a little bit more intuitive. So we said F2, let us say is ILF1, and then we knew this won't work. So there is nothing weird about it. So F2 equals ILF1 doesn't work because not both quantities are orthogonal. It turns out that F2 and F1 then are orthogonal, but F2 and F0 are not orthogonal. That's what happens. So now you have to add something to F2 equals ILF1, which is what we first thought we'll try. And let's call it X1. And now if you take this F2 equals ILF1 plus X1, and again see if this F2, this new F2 will be orthogonal to F1 and orthogonal to F0, then you begin to see that yes, that is possible, but that is only possible provided either of these two choices have to be satisfied. One is that X1 is some constant times A. Wait a minute, somebody having trouble with the video? I was getting a message that somebody was having trouble.
Yeah, me.
Oh, what happened to you?
I don't know. The connect of the internet is very weak.
Oh, okay. How much did you miss?
Just a few minutes. That's all.
Oh, okay. Anyway,
Yeah.
I'm recording it, so I'll be posting it. Okay, so you can take a look at that. Yeah. All
Okay,
right.
thank you.
Okay, sure. So so now what you do is you assume this x1 is somehow c times a. A is same as f0. Remember, this is the dynamical variable at t equal to 0. So this is one choice, and turns out this is the right choice. The other choice is x1 is some constant c prime il squared acting on a. If that is the case, then also it works. But let's see what happens. Try the simple choice first. Always try the simple choice first. That's the Occam's razor principle. Never try the complicated choice first. So if you work out the first choice, first choice, then you will see that this delta 1 turns out to be this constant, what we call delta 1, turns out to be a dot over AA. This is F0 over F1 over F0. So scalar product of F0 comma F0 in that Hilbert space physically means it's the length square of F0. Scalar product of F1 comma F1, which is what this is the length square of F1. So what the system is telling you, this first choice is telling you, is that this C is F1 square over F0 square in that Hilbert space. So therefore, if F2 is this, then it will work. If F2 is this, then it will work. Now, what about this choice? Okay. That choice, if you do, you can still get it to work, but you run into a strange problem. Your F2 becomes equal to 0. There's a problem with that. The problem is then you have F2 equal to 0. Essentially, that means you have a two-dimensional Hilbert space. Nu equal to 0 and nu equal to 1. These two terms survive. Everything besides that is going to be 0. That's what it means. So what is the problem with this finding? Any of you have any ideas about that?
I believe it's an extra constraint because we're now in like we've reduced our dimensions.
Yes. That's, yeah, you're absolutely right. This is, in fact, you had asked this question. So you can over constrain the problem. So in this case, what happens is that you are forcing all dynamics to be in 2 dimensions. In 2 dimensions, you can only have 2 frequencies. We know very well that not all dynamics can be described by 2 frequencies. So in other words, this turns out to be a choice that violates our completeness assumption. We assumed that A of t equal to this whole sum, nu of t f nu, it's a complete series, whatever that complete means. But now we are coming back and saying, oh, it's a series with only 2 terms. We are violating our own initial principle. This doesn't work. So at the end of the day, you can generalize the expression we have found. So f nu plus 1 is il f nu plus delta nu f nu minus 1. Delta nu is the length square of f nu divided by the length square of f nu minus 1. So delta nu therefore involves, let's say nu is level 7. It involves f7 square, the length square of f7 over length square of f6. Now you can wonder and say, what happened to all the other f's? It turns out, and this you will see in the final exam when you work on it, that the lower f's actually get sucked into the higher f's. They are built in strange geometric structures. So therefore, the information about the lower f's are needed to build the higher f's. So that information is there. But this delta nu also, it means, has a geometrical significance in that Hilbert space. So delta nu tells you a little bit about the hypergeometry of this space, if you will. All right. So any questions so far? Okay. If you have questions, just actually don't raise your hand, just unmute yourself and ask me, because if you raise your hand, I won't be able to see it. Jeff, you are blowing a bugle. What's up with you?
That was just my happy reaction.
This is not the cause for that level of celebration. Okay. So, all right. So now it turns out that this particular recurrence relation is a three-term recurrence relation, obviously, right? Now, the reason why I'm making an issue out of it is because you get recurrence relations of a variety of terms, all right? So a recurrence relation like the first one here, the trivial one, F1 is ILF0, this is a trivial recurrence relation. This one is the first non-trivial recurrence relation, three-term here. And it involves three levels. F nu plus 1 involves F nu and F nu minus 1. And that, of course, is captured here as well. Now, the thing is that three-term recurrence relations have certain mathematical properties, and they are nice. So we are lucky to have them, and we'll reap their benefits soon, as you will see. So in general, then, you can write it in this format, provided you understand that there is no such thing as f of minus 1, because the series starts at nu equal to 0. So f of minus 1, you have to by hand set it to 0. And f of d in d-dimensional space is by definition 0. Also, the lowest delta you can have is delta 1, and the highest delta you can have is delta d minus 1, because if fd is 0, delta d will be 0, obviously, because you can see delta nu is length square of f nu on the top, over top. So anyway, so this is the property that you have of the first recurrence relation. Now, knowing the first recurrence relation just gives you the f's. What about the a's? What about the time-dependent behavior? So the Liouville equation is about solving time-dependent behavior. So now we have to go back to the Liouville equation, and the Liouville equation is here, right? And we know that we can write this A of t as our as our series. So then A dot, the left-hand side, is nothing but nu equal to 0 to d minus 1, A nu dot, because this is the only time-dependent term, times f nu. So that this should not confuse you, because you don't have any time dependence in f nu. So this is equal to nu equal to 0 to d minus 1, A nu of t, but f nu is now IL f nu. So IL f nu, why? Because this is IL AT, right? So that's the right-hand side of the Liouville equation. So what we are doing is we have taken the series we have constructed, and we are now substituting it back into the Liouville equation to see what happens. So at this point, IL f nu is something that we know how to calculate, because the recurrence relation that we derived, which is f nu plus 1, is IL f nu plus delta nu f nu minus 1, can now be written as IL f nu is equal to f nu plus 1 minus delta nu f nu minus 1. So that's exactly what we do. We write A dot, okay, we write A dot here. Then we write the right-hand side, this term, now as the difference between the two terms, which is this term minus that term, see? But we have to be a little bit smarter. What we do here is we change the summation here from nu equal to 0 to d minus 1 to 1 to d minus 1, because if then the a0 and change this a nu to a nu minus 1, because then it turns out that the series is represented in a more convenient way. And then if we define a of minus 1 to 0, we can change it back to nu equal to 0 to d minus 1. So we have just done a little bit of gymnastics to write this particular statement in a slightly different form, which is this form. So now you see this nu equal to 0 to d minus 1 a nu dot of t f nu is here. And the right side, which is this side here, is here. So therefore, we write nu equal to 0 to d minus 1 a nu dot of t f nu equals 0 to d minus 1, and then this piece here. And since there is term by term connection, we can drop the summations, and we can write by putting it on the left side and getting rid of the f nu's. Delta nu plus 1 a nu plus 1 t is equal to minus a nu dot. So this goes to the left, that goes to the right. So minus a nu dot plus a nu minus 1 t. This is now your second recurrent solution. So if you think about it, by constructing the f's that you have constructed, and by substituting the f's into the Liouville equation, you have pulled out a recurrent solution for the a's. That's what you have done. And because you are trying to solve the Liouville equation, this recurrent solution for the a's actually is what gives you the solution to the Liouville equation, because this is where all the time dependence is. So therefore, if solving the Liouville equation is difficult, all your difficulty is embedded in the second recurrent solution. So let me ask you guys a question. Who wants to answer this? Some brave soul is needed as to what is wrong with this recurrent solution. There's nothing mathematically wrong with it. So don't think along those lines. When I say what is wrong with this recurrent solution, what I'm really asking is what is especially difficult about this recurrent solution.
Units are wrong.
Huh?
Wrong units,
Why?
because there is some time derivative of a term plus the term itself, or
No, units are not wrong actually. Units are fine. There's nothing mathematically wrong.
Is it hard to find like the first mu, or like find a dot mu?
Yes. Yes. The whole thing is upside down. Just stare at it. To know A0, you have to know A1.
Well, that sucks.
To know A0, you have to know A1. To know A1, you have to know A2. To know A2, you have to know A3. So what is the system trying to tell you? Something pretty serious it's trying to tell you. Who wants to take a shot at it? Okay, I'll tell you the answer to that. The system is trying to tell you that you cannot solve for these time-dependent coefficients sequentially, which means you have to solve for all of them simultaneously, because there's no other choice.
So you have to construct a vectorization of it and probably take an inverse matrix transform to do it?
Yeah, that's one possible avenue, of course, but there is a better avenue. or purportedly better revenue. So what it is, okay, a couple of things. First is that, okay, before I proceed further, you can pull out some general properties. First is by construction, A0 of t equal to A0 at t equal to 0 is 1, because left side is A at t equal to 0, which is F0, and the right side is F0. You can't have any other terms. So A0 of 0 must be 1. And secondly, A nu of 0 is 0, of course, that goes with it. And thirdly, you can show that time reversal invariance requires A0 dot of 0 is equal to 0, which means that for relaxation functions described by A0, which are always 2-point relaxation functions, 2-point meaning like AT, A0, you can't have a pure exponential solution for all times. You can have a pure exponential decay solution for late times, but you can't have it for all times, because this condition is untenable with this statement. So whenever you see relaxation function described as an exponential function for a correlation function, and I'll tell you more about that in detail, it necessarily means that that is not valid at t going to 0. It is valid later in time, but not at t going to 0. So there is a lot of important stuff on this, including this paper in 1983 about properties of autocorrelation functions, which is what A0 of t is. All right. Now, let me move on a little bit. Okay, go back. Let's come here. So I told you this is the first level of the relaxation function. Sorry, of the relation between A1 and A0. So let us take a Laplace transform of this. So for those of you who are not very comfortable with Laplace transform, let's say, the difference between Laplace transform and Fourier transform is difference between tea and coffee. They both do roughly the same thing in a little bit different ways. So Fourier transform is a hammer that we are more used to using. Laplace transform we somehow use less, but Laplace transform can also be exceedingly useful. And in most cases, they do about the same thing. So if you take a Laplace transform, the properties of Laplace transform are such that a derivative becomes like this. So f dot in t is z f dot in z minus 1. That's what it is. So this is a1 of z. You go from time to z. Z is basically I omega. And so you go in frequency domain, basically. And so this is the form it takes. And for nu more than 0, so nu equal to 1 or larger, then you get this structure. Nu minus 1 of z equals z nu plus delta nu plus 1 nu plus 1. Now you can do something. What you can do is you can rewrite equation 1 here in this form. As you can see, both sides are being divided by a0. So it's delta 1 a1 over a0 plus z minus 1 over a0. And then you pull the 1 over a0 to the left, and then you are left with this on the right. And then if you flip it to just a0, you get this structure. And then you can construct an a1 over a0. A1 over a0 comes out in terms of a2 over a1. And then if you want to simplify it further, you can write it in this form, which doesn't look very simple. But if you go back to a0, you can start to see this form emerging. And then if you start replacing this a2 over a1, you start to see this form emerging. This is called a continued fraction. So the suggestion, David, you made about doing a matrix inverse, that is not very different from basically a continued fraction formulation. In this case, if you have an infinite number of deltas, which is the case for most systems, you have an infinite series in your continued fractions. But you shouldn't get too nervous about it. Suppose all these deltas are 1. Then you can trivially solve this continued fraction because you can write the repeating levels. There's work going on. There's a lot of background noise. I'm sorry. So you can write the repeating levels in terms of a recurrence relation and actually sum up this continued fraction in that case. But continued fractions in general are not easy to solve. There is a very, very interesting book by Wall, W-A-L-L. It was written in 1948. And it's one of the authoritative books on continued fractions for those of you who are interested. It's a branch of mathematics that is quite specialized. So
Normally when I see them in Mathematica, I just assumed I did something wrong, but so much for that.
yeah, continued fractions are extremely powerful. So in general, if you can formulate a function that you want to calculate in continued fraction form, it either is a very good investment or it's a terrible investment. It's a very good investment when the deltas are well behaved, meaning that they grow in a certain way. Usually these deltas grow. Now, if a delta D becomes 0, then of course it's a finite continued fraction, which makes it quite trivial. But in general, these deltas grow. So how these deltas grow decides how manageable the continued fraction is. And if the growth rate is not very high, then the continued fraction is convergent. If the growth rate is high, then the continued fraction may not be convergent. That doesn't mean it cannot be summed, but it won't give you a convergent series. If you don't get a convergent series, that doesn't mean it's a divergent series. That means it's a non-convergent series. Okay. So if you now take this and expand it out, this is how it's going to look like. A0 of z is 1 over z minus delta 1 over z cubed plus delta 1 plus delta 2 over z fifths and so on. This is actually a frequency expansion because z is frequency basically. So this is therefore a high frequency expansion. If z is large, which is frequency is large, then this is a small number. So this is a high frequency expansion. High frequency expansion is like a short time expansion. So if you go term by term and go to time domain, you get this even series in time as you should, accepting that these coefficients that you get are not your short-term coefficients that you could have gotten. These coefficients are drastically different, right? So this is a little bit about the continued fraction. Let me see, I think I made a few statements about the continued fraction here. Yes. So if you have a finite number of levels, so if d is less than infinity, finite number of levels, then your A0 of t is necessarily of this form. So it's a bunch of frequencies. So therefore the problem cannot be that bad, right? It can be bad, but not that bad. It also tells you that if you have a finite number of frequencies, your A0 of t as t goes to infinity can be 0. It's a bunch of cosine terms. How can it be 0? So in other words, your system never relaxes. It always remains hyper, which means that the energy doesn't disperse out to the whole system, which means the system is non-ergodic. That is the definition of non-ergodicity, non-ergodic system. Now, if your d goes to infinity, then all bets are off. This is most often the case. Suppose your d goes to infinity, And suppose your deltas, which, as I said, grow in general, they're growing at some rate new to the phi, where this phi is linear or sublinear, less than 1. So it can be like this. It can grow quickly and then stabilize in some way, shape, or it can be linear. Now, linear and sublinear behaviors, you can always compute these continued fractions, even if you can't compute them exactly. And the way you do it is you replace the continued fraction, which has, let's say, infinite levels, by a finite number of levels. Now, if you say you're going to do it with 10 levels, that's going to give you a bad result. But if you want to do it with 100 levels, it's going to give you a better result. So we have, for example, done studies where we have gone up to millions of levels. And millions of levels gives you results that are really quite impressive. So this is the story of continued fractions when this phi is equal to 1 or less. However, there are systems where phi can be more than 1. And if phi is more than 1, then the continued fractions become non-convergent. And I will refrain from that discussion because we have recently solved a significant part of this problem. So I'll come back to it down the road, but not right now. It's not necessary. Maybe Thursday I'll tell you a little more if necessary. But in general, if phi is more than 2, there are problems. And phi can be more than 2 for strongly nonlinear systems. So for linear or linear-like forces, this phi tends to be typically of the order of 1. But if you have strong nonlinear forces coming in, then phi can be more than that. Can anyone tell me what is an example of a strong nonlinear force?
I want to say air resistance, because at low speeds, it has different forms depending on what regime of speed you're in.
Yeah, but it's normally you don't write it in terms of a potential type force, right? Think in terms of a potential type expression. Can you think of any system where there's a potential that you are dealing with, which potential gives you a nonlinear, strong nonlinear force? Okay, let me tell you. One example of it would be, I take two stainless steel balls and I press one against the other. The balls would repel, right? So this repulsion turns out to be a pretty strongly nonlinear force. You can't describe it by spring forces. In fact, if you describe it by spring forces, your answers will come out quite incorrect. So that's an example of a strong nonlinear force. There are many material systems where you have strong nonlinear forces. If you have atomic scale interactions, for example, one standard way of describing them is via Leonard-Jones interactions. Leonard-Jones interactions actually would also be an example of nonlinear forces. So nonlinear forces, therefore, arise in nature quite a bit. And if the nonlinearity is strong compared to harmonic forces, then you run into this problem of phi getting towards 2. If this is weak compared to harmonic forces, then you run into the case of phi being of the order of 1. That's just to give you an intuitive feel for it.
Dr. Sen, I have a quick question for you.
Yeah, go ahead, please.
I know a pendulum without the small angle approximation, so a pendulum I just bring super high up is
Right.
nonlinear. Would that be strongly nonlinear?
Yeah,
Okay.
yeah, that would be. Of course, this is in contact with the heat bath, right? Because you have a temperature in the problem. So here you have your pendulum.
Yep.
But this pendulum is connected to a heat bath
Mm-hmm.
to be able to see the corresponding physical problem when you have a pendulum with temperature.
Yeah. Would that be driven in some way?
It doesn't have to be driven. It can just be.
Okay.
In fact, because it'll be in contact with the heat bath, it'll become it'll relax.
Okay.
So that's also an important part of it. Hang on one sec. I'll be right back. One sec. All right. So let's see. I want to move on to something else, which is also very interesting. So if you go back to your second recurrent solution, which is what we have here, this is the same one that I showed you. And if you define a function phi of z, which by construction is delta 1 a1 of z over a0 of z. Delta 1 a1 of z over a0 of z if you do, and if you call it delta 1 b1 of z, just define it. Then you can rewrite this equation as just reorganized. ZA0 of z minus 1, the ZA0 of z and 1, and then phi of z, a0 of z. So this is your, then delta 1 a1 of z becomes phi of z, a0 of z, this thing here. If you do that, then if you take the inverse Laplace transform of this whole thing, you get the following integral differential equation. You get a0 dot of t, now in time domain, is integral 0 to t dt prime. And here is your old friend you have met once before, the convolution of this phi function with a0 of t prime equal to 0. Remember, we had convolutions in the Takahashi gas. So this is very similar. It's a convolution. So your a0 dot of t, your correlation function derivative, turns out to be relatable to this phi function and a0 of t prime as a convolution. And it turns out that if you define b news similarly, remember we defined this delta 1 b1 as delta 1 a1 over a0. So a1 over a0 was b1. Similarly, a nu over a0, suppose it's called b nu. I'll give you all these lecture notes so you'll have access to these. And if you then construct the same relationship, but instead of doing it for 0, you do it for nu, then you get the following relationship. A nu dot of t is integral 0 to t dt prime phi t minus t prime a nu of t prime equal to b nu of t prime. Now you might be wondering, why is Dr. Sen spending so much time telling us about this particular equation or that equation? They don't look particularly nice because you have an integral here, you have a convolution here. Why do I care? Okay, I'll tell you in a moment why you might be interested in this structure that I'm trying to show you. Suppose now I do nu equal to 0 to d minus 1, and I add all these equations, all of them. So the right side will be a little bit special because in this case, the right side was 0, but here is this b nu of t prime, but this b nu is this guy. This is b nu of z. So you have to take a inverse Laplace transform to go to t here. So it turns out then that I can write this combination of all the a's and nu equal to 0 to d minus 1, a nu dot of t f nu. I'm multiplying by f nu because I have to do the whole sum. Phi t minus t prime nu equal to 0 to d minus 1 a nu of t prime f nu. And then nu equal to 1 to d minus 1 because the first term is 0. B nu of t f nu. Let's call it f of t. Let's call it f of t, whatever this is. We don't know what the series is. However, we know what this is. This is your a dot of t, big A dot of t. So I can actually write it in the following form. A dot of t equals 0 to t dt prime, phi t minus t prime, a of t prime. Why? Because if you go back, this is your a of t prime. This guy is a bit different. So we can write this f of t that we constructed, we defined. And this f of t is nu equal to 1 to d minus 1, b nu of t f nu. Suppose I give it a name, random force. This is a historical name. This name, I don't think it has a big meaning in terms of force, but it's a historical name. This equation, this integral differential equation, is a very interesting equation. This equation has no information which is more or less than the Liouville equation. Just absorb what I said. So this equation here says the exact same thing as the Liouville equation, excepting Liouville equation is an equation with Poisson brackets, whereas this equation is an equation with a phi function as a convolution. It's an integral differential equation. This phi function has a very important name, reminiscent of what this phi function is. It's called the memory function. And in fact, it measures the equivalent of how often a system remembers or how long a system remembers its interactions. So suppose a system remembers its interactions over very long times. Then the memory function, this phi function, is very long-lived. But suppose the system forgets about its interaction very quickly. Such systems can be easily modeled by thinking about this phi function as a delta function. This is what is known as stochastic approximation. So in a stochastic approximation, life is very simple. You forget about interactions very quickly. And this is the reason why stochastic approximations simplify problems. In fact, stochastic approximations are undesirable. They are unphysical. They are used a lot, but they're undesirable and unphysical by and large because they oversimplify the effect of interactions over time. In fact, if you put in this function, then it turns out your generalized Langevin equation, which is what this equation is called, which is the same as the Liouville equation, as I told you. This generalized Langevin equation becomes what is called the Langevin equation. And then this gamma term, which comes out of this stochastic approximation, becomes the equivalent of a friction or viscosity. So what I have taught you today is something which I think is really remarkable. It shows you that you take the Liouville equation, and by constructing the solution the way we did, you can recast that Liouville equation as a generalized Langevin equation. This generalized Langevin equation has a memory function. This is the phi function. And if you could figure out the memory function of a system, then you can from that construct your A of t. Now, some of you will ask, what about the f of t? That's a problem. This f of t is this quantity here. And of course, we know theoretically how to calculate that using the continued fractions, right? But the long and short of it is, yes, while we can calculate that, it is a hard thing to calculate. And furthermore, its net effect is as if you have all kinds of interacting random forces. That's the net effect. That's why it's called a random force. But this random force is absolutely non-random. It's purely deterministic. All right, any questions before I move on to the next point? How many of you I have lost? Tell me.
I'm hanging on by a thread.
Yeah.
Yo.
I don't think I've ever not been lost.
What about other people? Danielle, are you lost?
Yeah, just trying to catch up.
So
Nathan, you are there?
we have problem on this on final, right?
What?
We will have problem on this in final, right?
Yes,
Okay.
should be fun. I promise you. So
I guess fun for you only.
it'll be fun for you too. I will not give a difficult problem. All right, so let me switch gears and let me take you to something else. So what I'm going to tell you is about a work I did many, many years ago, probably before each and every one of you were born. Can you see my handwritten stuff here?
Yep.
Yeah.
All right. So this particular calculation that I'm going to briefly try to talk about today and Thursday, I did back in 1990. And there is a pretty detailed paper on this that I wrote. And this is the paper, PhysRef volume 44, 1991, page 74, 44 onwards. And this talk I originally gave somewhere, I don't remember where anymore, on 13th of December, almost 31 years ago, 1990. So let me just tell you a little bit about this work. As you can see, the title of this work tells you it's spin dynamics in an S equal to half. So it's a quantum spin system in a semi-infinite XY chain. Now, that is not something you expect to know. Nor did I when I did this work. I invented the system, sort of. And then a lot of things followed. But I was fooling around with trying to learn the continued fraction formalism at the time. I had some background in it. But I figured that one of the simple non-trivial systems I can work on is this XY chain. I've referred to the XY model in class, but let me show you what the XY model is briefly. Forget about these two terms. Just focus on the first term here. So the Hamiltonian describes a spin chain, just an alignment of spins, and the I and the I plus 1th spin, so the nearest neighbor spins, they interact. And the X spins, the X and the Y pieces of the spin interact, the Z pieces don't. So that's why it's called an XY model. It's a pretty dumb origin of the name, XY model, because the SX, SX, and SY, SY terms are there. So what I wanted to do was I wanted to see that instead of studying the full XY, infinite XY chain systems spin dynamics, let's say at some jth site, what if I study the spin dynamics of the same system if there is a defective bond here? Okay. So this particular spin is therefore linked to the jth spin and the j plus 2th spin by different bond strengths. That's what I have modeled here. And as I was doing this, it occurred to me, what if I actually arrange for this j prime x and j prime y to be such that this spin is subtracted off completely? It turns out, obviously, that is equivalent to cutting this infinite chain here, which means it makes it a semi-infinite chain. It starts at j, but then goes on to infinity on the left, but it doesn't go any further on the right. And then I can ask the question, what about the dynamics of the jth spin? XY model, not Heisenberg model. So, you know, when you play around with things, you have nothing to do, you're a postdoc, these kind of ideas pop in your head. And this was the idea that popped in my head one day. And so I went around and did some scouting. And I found that indeed there are physical systems that can be used in the laboratory to actually design the kind of system I was thinking of. In those days, it was harder. Now it is much easier. This is a cesium, cobalt, and chlorine compound. This is a praseodymium and chlorine compound. And this is the same compound almost with some water. There's some examples. So just to give you some background, for the infinite XY chain, there were a few major results that were around at the time. The first one was by Niemeyer. Niemeyer was a very famous statistical physicist from Denmark. And he showed that the Z spins, the dynamics of the Z spins, this correlation function at high temperature could be solved. Exactly. A very famous result. And then this fellow here, Jacques Perk, he was a graduate student of Henk Capel, who was also very famous. He did his PhD work on looking at the X spin in the exact same problem. So just to give you a sense then, this is a XY model. If you set Jx equal to Jy, or if you don't even set that, the Z spin is therefore symmetrically interacting with X and Y. So the Z spin's dynamics would be a little bit easier than the X or the Y spin's dynamics. So therefore, one could see that Niemeyer's result would be easier to get than Capel and Perk's result. And indeed, that's the case. It was a decade separating these two major results. And then at some later time, there was an important approximate result by this fellow, Gerhard Muller. Gerhard Muller is a professor at Rhode Island. And this was his postdoc advisor, Bob Schruck from Stony Brook. They prepared this study where they approximately solved the Capel-Perk problem, but at low temperature. Low temperature physics is harder. So this was an important result, again, 8 years later. This is just to give you background. So I thought that nobody had looked at the semi-infinite chain, and what could I do? Could I get something interesting and learn something from it about the continued fraction approach? And to make a long story short, I did learn a lot. And I'll tell you what I learned, and then I'll walk you through the study in more detail on Thursday. So if you remember, the Liouville equation has this form. Again, I haven't used the I here, it should be an I. In those days, I was still defining things my own way. So this is the Liouville equation. This is for the quantum mechanical case, you have a commutator bracket, H bar is set to 1. And this is the standard thing that I just showed you. You can see I'm walking you through all the steps. The first recurrence relation is writing capital delta equals small delta. And this is the second recurrence relation, continued fractions, and so on. I didn't take you to the inverse transform, but let's not get into that now. So it turns out, my question was, can I solve the Liouville equation just for this operator, Sxj of t? So just to be clear, Sxj of t, the dynamics of that operator as described by Liouville equation. So dsxj of t dt equals I over h bar Hamiltonian comma Sxj commutator bracket. That's the problem. Can I solve it? The answer is yes, I could solve it, and I could solve it completely for the operator problem, which means that this is the only non-trivial problem in existence in the world, as far as I know, where a quantum mechanical operator problem is solvable. That's why that paper is pretty well known. So, and it was a coup d'etat for me, because I just got plain lucky. So what I did was, I took my F0 to be Sxj at t equal to 0 Sxj, and then I set temperature to infinity, which means I made these calculations trivial. In fact, if the temperature is infinity, this becomes a fluctuation formula, as I said before. And the fluctuation formula for Sxj squared, you can directly compute, it's just 1/4. Because each spin carries a 1/2 h bar is 1, so half times half is 1/4. So if you now use recurrence relation 1, you can actually generate all of these f's exactly. F1, F2, F3. Not only can you generate all the f's, you can also generate all the deltas. And you can see how these deltas go. Delta 1 is jy squared over 4, delta 2 is jx squared over 4, delta 3 is jy squared over 4. Just keep alternating. And in general, this has never ever happened to me after this. I could calculate all the infinite f mu's. This is it. So the paper has a typo. One of these is labeled wrong in many places. But this has no typo. This is my handwritten notes from those days. And here are your deltas, and I can exactly sum up the continued fraction. And I can tell you that the answer is A0 of t. J1 is a Bessel function of first order over Jt. And if you look at its asymptotic behavior, this behavior has a t to the minus 3/2 behavior in it, which is called a long time tail, because that's like a tail that goes on like that. So this is your behavior of an anisotropic XY chain, but Jx and Jy are not the same. But if you take an isotropic chain, I don't know where I put that. This is the isotropic chain. Let me see. I've forgotten this a long time ago. Actually, the isotropic chain. This is the nearly isotropic chain. This is actually a first order Bessel function. And as you turn on the anisotropy by weakening Jx or by strengthening Jy, you begin to get all kinds of oscillatory relaxation behavior. So all these were published in that paper, and you can take a Fourier transform and so on. But this is the pictorial dance of it. So you can see this is the surface spin, and this is the semi-infinite chain. And in operator lingo, for whatever it's worth, it's like you invoke the X spin, you just turn it on. This X spin, because of commutation relations and the XY Hamiltonian, activates a Y spin at J-1, goes back to the Z spin. This one activates an X spin in the next time step. These two go back to Z. This one activates a Y, everybody goes back to Z. And you can draw out the basis vectors schematically for the entire infinite system. You can calculate your A news. You can calculate everything that you want to calculate. And the problem is exactly solvable. So I could recover all the results, and so on and so forth. But let me stop here because we are out of time. If you have any questions, you can ask me about this. The only complete operator equation, Heisenberg operator equations dynamics, that I know has been solved in the world. And since 1991, it hasn't changed as far as I know.
Well, I guess in short, that at least answers the question I've always had, which is why I don't see more Heisenberg operator dynamics. And they bring up the picture and they're like, there it is, have a good one.
Yeah.
But I guess if we just haven't solved them, then that answers that question for me.
The whole field is sitting in front of you. You can keep on solving them for the rest of your life. I tried to solve a few more, but these problems are difficult. But you learn so much because it gives you the actual, detail of how the system is behaving when excited. And this is a purely quantum mechanical system in which you have the capability to calculate everything you want to calculate, which is astounding. All right. So anybody else have any thoughts? Have any sighs, cries? What a silent bunch. Everybody has fallen
No,
asleep.
everything is fine. Thank you.
Yeah.
Everybody has fallen asleep. Jeff is still showing his bugle
Yeah.
or whatever. Whatever. All right, guys. So I'll see you on Friday, and I'll give you the final exam after that. Friday, I'll get into this in a little bit more nitty-gritty.
Thursday.
Thursday, yeah. I don't want to see you Friday. All right. Bye, guys. Thank
Have
you
a good
so
one.
much.
Bye. Have a good one. Have a good
You
day.
too.
Thank you.
Bye.
Okay.
Thank you,
Bye-bye.
Dr. Sen.
Thank you. Thank you. Bye-bye.